Cloud. Okay, take it away.
Yeah, okay. So, hello, everybody. So, I am Ayoub. I am from Morocco. I have just started a PhD at UNIL University here in Switzerland. And I want to thank you for having me today. So, what I will be sharing is what I have been working on this summer in ECMWF Code of Earth edition. And that is like the compression of geospatial data with varying information density. I'm grateful for the guidance and supervision provided by Hauke, Milan, Juanjo, and Miha throughout the course of this project. So the exponential growth of data across multiple fields has created the demand for efficient data management. According to the ECMWF, an astonishing 300 terabytes of atmospheric data are being added to the archive on a daily basis. Also, according to the ECMWF, its data archive is rapidly approaching the exabyte mark. The present question is, with this exponential growth, where will the data archive stand in just a few years? Will it enter the Google regime? And furthermore, the graph underscores the critical role of compression, as portrayed by the green dots on the graph that represent a 10x and 100x compression. So data compression, also known as source coding of bit rate reduction, relates to encoding information using fewer bits than the original representation. It offers several advantages, including saving storage space, reducing bandwidth requirements, and improving overall system performance. So the data compression involves a trade-off between precision, size, and the compression speeds. Concerning the precision, it is different than the information content. One example will be someone measuring temperature in his backyard at 6 or 7 decimals. It is very precise, but not enough information to get the temperature across the whole city. So the goal is to achieve optimal results in all aspects. However, in practice, the aim is to strike a balance that suits the requirements of the application and the available resources. So this summer, I have been working on the bitwise real information content-based compression that is done as follows. The bitwise information, that is the mutual information between the bits, is calculated. And a bit position contains more real information. The stronger the statistical dependence to the adjacent bits it is, then we keep only the bits with real information and discarding the bits with false information. After that, we apply our lossless compression. I will go through the bitwise real information content-based step by step using this graph from Clever and Al paper. We assume working with the graded data and utilize a binary representation for efficient storage. So for the binary representation, we have the first bit in gray here reserved for the sign. If it is 0, the number is positive, otherwise the number is negative. The next set of bits represented by blue represents the biased exponent. It controls how far and in which direction to move the decimal points in the fraction. And the remaining bits in orange represent the matesa, also known as the significand or fraction. These bits represent the fractional portion of the number in binary form. Then we analyze the mutual information of adjacent bit positions. As an example, let's focus on the sign bit and examine the spatial distribution of all sign bits. When we look at one bit, we inquire about its significance in relation to its neighboring bits. And thus, we have more mutual information if the bits have something in common, and less mutual information if the bits just appear randomly. And we do that for the exponent bits and matesa bits to identify the key bits, which are the significant bits that preserve 99% of real information or any other wanted percentage. Finally, we remove the false information bits by rounding them to 0, ensuring effective compression without substantial data loss. So in this example, we have a one-dimensional bit stream of the data in binary representation. I have added some guides here to remind you of the bits order, sine, exponent, and mantissa. And using the concept of mutual information, we identify and retain only the significant bits. And the compression can be taught of something like this. And by applying this approach, we compress the data from 160 bits to just 60 bits. I will use some code to illustrate this. For this tutorial, I will be using xbitinfo, which is an X-array wrapper around bit information GL to retrieve and apply bit rounding from within Python. The package intends to present an easy pipeline to compress climate and other datasets based on the real information content. This package is mainly developed and maintained by Hauke Schulz and Aaron Spring. This is based on bit information GL that was developed during the summer of code at ECMWF editions of the year 2020 and 2021 by Milan Klöver. So the dataset used here for this example is the 2-meter temperature in Kelvin from the ERA 5 dataset. You can get it from the Copernicus climate data store. And the data type used is float 32. First thing is getting the information content per bit. For that, we use the get bit information function that calculates the information content for each bit, the sine bit, the exponent, and the mantissa bits. As we can see, the sine bit, the exponent bits, and the mantissa bits. As we can see, the first bits contain no real information. Then the values start relatively high and start decreasing near the end. Yeah. And to discard the bits without information, we need to have the key bits that refer to the number of bits from the mantissa that are necessary to retain. Approximately 99% of the information in this example. In this particular case, the key bits value is calculated to 8 bits. This value is then utilized to round the original data. So in this slide, the original size of the dataset was of 64 megabytes, which can typically be compressed to approximately 34 megabytes, resulting in a compression ratio of around 2. However, when compressing the bit rounded data, it results in a size of 4.1 megabytes, achieving a compression ratio of approximately 15. So in this summer, I have been working on the development of an information density adapting compression by implementing compression and bit information retrieval on a chunk basis and analyzing information density of climate variables across space and studying the optimal chunk size depending on specific features like hurricane. So we applied this chunking across latitude and longitude on multiple climate datasets. We started by exploring the effect of chunking on hurricanes using the ERA 5 data. We analyzed this timestamp where the Dorian hurricane had occurred. We have explored in this case the wind speed variable, and as we can see, we have some strong winds in the southern oceans, and one chunk with the Dorian hurricane as shown here. Even with this extreme event, we did not observe any significant differences in the variance of key bits value for the chunk with where the hurricane had occurred. And also we explored the direct solar radiation. In this plot, we observe variation in values across latitude and longitude. And when applying the bit rounding to the entire dataset, it employs a total of 12 key bits for keeping 99% of the information of the full dataset. And by utilizing chunking, we observe a spectrum of key bits value. And by varying from none in some chunks, like in the Arctic, to a maximum of 15 in other chunks. And regarding the disk storage utilization of decompression of bit-rounded chunks, it's noteworthy that it has accomplished a storage saving of 59 megabytes compared to the dataset bit-rounded and compressed as a whole. And this efficiency is further amplified by the fact that we are retaining higher precision, which when it is where it is more crucial. Among the other variables we have examined, there is the convective precipitation. In this plot, value disparities are apparent across also latitude and longitude, and bit rounding across the complete dataset have been done utilizing 8 key bits to maintain 99% of the information in the full dataset. And with the chunking, it reveals a diverse range of key bits value, with some chunks having no key bits, while others store as many as 12. And for the compression by the bit-rounded chunks gives similar results as compression the dataset as a whole. And the chunking strategy prove advantageous by preserving high resolution, high precision where it is needed. And we try to apply the chunking on multi-level datasets. In this plot, we are exploring one variable that is the specific humidity, but at different vertical levels. We see the variability in values across both latitude and longitude, and also by level. Like in the subplot A at 1000 hectopascal, namely the surface of Earth, there are low values in the Arctic and Antarctica, rising smoothly toward the equator. In subplot B at 500 hectopascal, we start seeing the turbulence of the atmosphere all around the globe. In subplot C at 100 hectopascal, some turbulence, but mostly near the equator only. And finally, at subplot D, the highest level, we can see like there is just a small portion near the Arctic that is different. And this slide, we delve into the variation of key bits distribution among different vertical levels. In the left side, an illustration to help understand what these vertical levels are like, assuming dry air at constant temperature. We have the Everest being at almost 9 kilometers at 300 hectopascals, airplanes flying at 12 kilometers at 200 hectopascals, and atmospheric balloons at 40 kilometers at 7 hectopascal. As we can see, the distribution of key bits varies depending on the level, with the prime illustration being the specific humidity variable in the purple color. However, it is important to note that this phenomenon doesn't hold true for all variables. For instance, the temperature variable in orange color, which have a consistent distribution across various levels. And for the implementation, one approach to put the chunking concept into action involves leveraging the ZAR's chunking capabilities and block features. As demonstrated in this slide, accomplishing this task can be achieved with just a few lines of code. And for a summary, like the bitwise real information-based content compression is executed as follow. We first calculate the bitwise information and keep it. We secondly eliminate the bits lacking real information, and we perform the lossless compression. And bit rounding the chunks before compression can enhance the compression by getting more details where needed without taking up more disk storage. And if you have a dataset and curious to know if you can enhance its compression, try it on xbitinfo.read.io. And this is my last slide. Thank you for listening.
Awesome. Let me stop the recording.